Welcome to this video on differential equations. In this video, we will explore the basics of differential equations, their types, and their applications in various fields. Differential equations are mathematical equations that involve derivatives. They are used to model real-world phenomena such as population growth, heat transfer, and fluid dynamics. Differential equations are used extensively in physics, engineering, economics, and other fields. There are two types of differential equations: ordinary differential equations ODE and partial differential equations PDES. ODE involve only one independent variable, while PDE involve multiple independent variables. Differential equations can be classified based on their order, linearity, and homogeneity. The order of a differential equation is the highest derivative present in the equation. A differential equation is linear if it is of the form nxy nx plus n-1c n-1x plus a 1x plus a 0x equals fx, where nx n-1 a 0x and fx are functions of x. A differential equation is homogeneous if fx equals 0. In the next segment, we will discuss the solution of first-order differential equations. In this segment, we will discuss the solution of first-order differential equations. A first-order differential equation is an equation that involves the first derivative of a function. The general form of a first-order differential equation is dx equals fx, y, where y is the dependent variable and x is the independent variable. The solution of a first-order differential equation is a function x that satisfies the given equation. There are several methods to solve first-order differential equations, including separation of variables, integrating factors, and exact equations. The separation of variables method involves separating the variables x and y on opposite sides of the equation, and then integrating both sides. This method is applicable when the equation can be written in the form dx equals g xh y. The integrating factor method involves multiplying both sides of the equation by an integrating factor, which is a function that makes the left-hand side of the equation the derivative of a product. This method is applicable when the equation can be written in the form dx plus bxy equals qx. Exact equations are a special type of first-order differential equation that can be solved by finding a function x, y such that do/dx equals fx, y plus f/u. The solution of an exact equation is then obtained by integrating x, y with respect to x and adding a constant of integration. In the next segment, we will discuss the solution of second-order differential equations. In this segment, we will discuss the solution of second-order differential equations. A second-order differential equation is an equation that involves the second derivative of a function. The general form of a second-order differential equation is d2y/dx2 plus px dy/dx plus qxy equals fx, where px, qx, and fx are functions of x. The solution of a second-order differential equation is a function x that satisfies the given equation. There are several methods to solve second-order differential equations, including the method of undetermined coefficients, the method of variation of parameters, and the Laplace transform method. The method of undetermined coefficients involves assuming a particular form for the solution and then finding the coefficients that satisfy the equation. This method is applicable when the equation has constant coefficients and the right-hand side is a polynomial, exponential, or trigonometric function. The method of variation of parameters involves assuming a general form for the solution and then finding the coefficients that satisfy the equation. This method is applicable when the equation has non-constant coefficients and the right-hand side is a polynomial, exponential, or trigonometric function. The Laplace transform method involves transforming the differential equation into an algebraic equation in the Laplace domain and then solving for the Laplace transform of the solution. The solution in the time domain is then obtained by taking the inverse Laplace transform. In the next segment, we will discuss the applications of differential equations in physics. In this segment, we will discuss the applications of differential equations in physics. Differential equations are used extensively in physics to model the behavior of physical systems. One of the most famous examples of the use of differential equations in physics is the Stinger equation, which is used to describe the behavior of quantum mechanical systems. The Stinger equation is a partial differential equation that involves the wave function of a particle. Another example of the use of differential equations in physics is the Navier-Stokes equation, which is used to describe the motion of fluids. The Navier-Stokes equation is a set of partial differential equations that describe the conservation of mass, momentum, and energy in a fluid. Differential equations are also used to model the behavior of mechanical systems. For example, the motion of a simple pendulum can be modeled using a second-order differential equation. The equation of motion for a simple pendulum is d2/dt2 plus g/L sin equals 0, whereas the angle of a pendulum, t is time, g is the acceleration due to gravity, and L is the length of the pendulum. In electrical engineering, differential equations are used to model the behavior of circuits. The behavior of a simple RC circuit can be modeled using a first-order differential equation. The equation for the voltage across a capacitor in non-RC circuits is dV/dt plus 1/RCV equals 1/RCVin, where V is the voltage across the capacitor, T is time, R is the resistance, C is the capacitance, and Vin is the input voltage. In the final segment, we will summarize the key points of this video. In this video, we have discussed the basics of differential equations, their types, and their applications in various fields. We started by introducing differential equations and their two types: ordinary differential equations ODE and partial differential equations PDES. We then discussed the classification of differential equations based on their order, linearity, and homogeneity. In the second segment, we discussed the solution of first-order differential equations using methods such as separation of variables, integrating factors, and exact equations. In the third segment, we discussed the solution of second-order differential equations using methods such as the method of undetermined coefficients, the method of variation of parameters, and the Laplace transform method. In the fourth segment, we discussed the applications of differential equations in physics, including the Schrödinger equation, the Navier-Stokes equation, and the equations of motion for mechanical systems and electrical circuits. Differential equations are a powerful tool for modeling real-world phenomena and are used extensively in physics, engineering, economics, and other fields. We hope that this video has provided you with a better understanding of differential equations and their applications. Thank you for watching.